Sure. Time stamp in 6. Mr. Moore. Please follow me. Hola, Mr. Frosky, you might want to leave by the teams.
Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
Good evening, all. We will start the session. Adil sir, good evening. Students, kindly inform your friends to join the session as soon as possible. We are starting for the day. Adil Yusuf sir, is I'm audible?
Yeah. Good evening.
Yeah, good evening, sir. You can take over the class.
Okay, fine. Thank you. Yeah, good evening, students. How are you all? Hope you are doing fine. Okay. So may I know where we left yesterday? Yeah. Selection sort, right? Okay, if you know, yesterday we discussed binary search, insertion sort, and selection sort. I guess selection sort we have done it or not? Yes, we have done bubble sort. Sorry. Yesterday we did binary search, bubble sort, and this selection sort, right? So today we'll be discussing other sorting techniques. So let us have a quick recap of yesterday's session. Binary search simply binary search is simply where we what? Search an element in a list, right? And the precondition for a binary search is that the array has to be sorted, isn't it? Right? Then we did an algorithm for that binary search. When the list is sorted, then we used to find the mid to designate the first element as low and the last element index as high. So then we will find the mid. Mid is equivalent to low plus high minus low divided by 2. That integer flow that we discussed. Because of that, we used to put low plus high minus low divided by 2, right? So that integer flow we also discussed. So after finding the low, this mid, then we used to compare the element that we want to search, the target element. And based on that, we used to travel either the left subarray or the right subarray. And based on that, we used to find the element. We used to search an element in that array. And as I already told you, the growth of this function is logarithmic because at every step we used to divide the array into two. Then we traverse only the half of it, half we like neglect. We don't care about that. Then again in the second step we again divide that subarray. Then so on and so forth. Means it is a logarithmic growth. That is why we are just saying the complexity of binary searches log of n. Right? After that, we discuss about sorting techniques. What are sorting techniques? And in sorting techniques, we discussed yesterday two sorting techniques. One was bubble sort and another one was selection sort, right? So in bubble sort, what we did? We simply traverse the element, right? Then we compare the elements. Whosoever is bigger element, that gets bubbled up. Right? Then again, we compare the next two elements in the past one. Whosoever is bigger, that gets bubbled up again till the bigger element gets bubbled up to the right in the first pass. Similarly, we will do the pass second, and we have to compare now only n minus 1 elements, right? So in pass second also, we will get the second largest element to the right, and this way we will get the whole array sorted. So in this way, what we are doing, we are actually sorting the elements in n minus 1 passes. And if you know, each pass is taking at least in the first pass, we are comparing the n elements and the number of comparisons is n minus 1. In second pass, we also have n minus 2 comparisons. And in third pass, we have n minus 3 comparisons and so on. Right? So with this way, when we try to add all these comparisons, it turns out to be n into n minus 1 divided by 2, or I can say it is of the order of n square. So that's why we are just saying that the complexity of bubble sort is n square. Similar is the case with selection sort. Here what we are doing, we are selecting an element index, comparing that, we are actually dividing the array unsorted part and the element. Then we take one element from the unsorted part, compare it with this, select the element whosoever is bigger, and this way we are actually doing what? We are comparing all the elements, are at the end we are getting a sorted list. And here also the complexity is of the order of n square, the worst case complexity. Yeah, do you know Gen AI classes? Yes, because most of the times I used to teach artificial intelligence, machine learning, generative AI, and data science. That is actually core area. Okay. So today, what we'll be doing, we'll be going with this insertion sort. Let me share the screen with you first. I hope the screen is visible to you, right? Yes or no? Just a confirmation.
It is visible, sir.
Okay, fine. Thank you. So what we are going to study right now, it is insertion sort, right? See, insertion sort is simple. It is like this, na, sorting a hand of playing cards, the playing cards that we have. How do we sort those playing cards? It is simple. So what we do, we usually choose one card, check its position and place it. Then we pick another card, check its position and place it. It is simply insertion. Pick a card, check its position, place it. Another card, check its position and place it. Same way this insertion sort is working. Means we are just picking one element at a time by inserting each new element into its proper position, or I can say the proper place in the sorted part. Means we have unsorted part and sorted part. Like suppose I will give you 10 cards and they are random. I just want you to sort these 10 cards. How do you sort? You will apply sorting techniques. You just place these cards like this. You will take the smallest card, right? Or you will take the first one. Check it. You will place it somewhere. Then you will take the second card. Compare it with all this. If it is like smallest, you will place it second. Then you will take another card. Compare it and place it. And this way, actually, we are doing insertion. So we are performing the insertion sort. And normally it goes from left to right. Because when you also play with those cards, we usually go with left to right. Means from index 0 to n minus 1, or I can say index 1 to n minus 1. Because it is comparing each element with the previous element. Means it is comparing, if I have the first element, now I want to compare the second element. What I will do, I will compare this second element with the first element. If it is smaller, I will place it left of it. If it is bigger, I will place right of it. So then I will take the third element, compare this third element with the first two and place it accordingly. Similarly, I will take the fourth card, compare it with the already sorted card that I have sorted, right? Then I will place it accordingly. So this way all the cards will be sorted. Right? Let me explain this example. See, it is simple. If we go with the algorithm, for I is equal to n minus 1, we'll select a key, ith element. Then simply I minus 1, we'll set it to j. Then we'll start using a for loop, while loop. And we'll start it till we will, while j greater or equal to 0, till and ARR of j is greater than key, the key that we have set. So we'll do it like this way. Then we'll perform the movements, or I can say we'll insert the element. This is the algorithm, but let me first give an example. We'll do with an example. Let us use this annotation. If you have any question, you can ask. It is simple. Let me take an example. For example, I will take 5, 2, 4, 6, 1, 3. So these are the elements, right? Now what I will do, I will start with pass 1. In pass 1, what I will do, I will set as per the algorithm. If you are checking the algorithm, I is equivalent to 1. Let me write like this so that you will not get confused by the algorithm. Right? I am starting with 1. So what does this mean? I am starting with 1 because I have selected this 5 as key, as the first element, 0th index. So I have to insert 2 into this. For example, now I have the sorted part as 5 and unsorted part as what? 2, 4, 6, 1, 3. Fine. Now I have to compare this I equal to 1, 2 with what? With 5, and I have to insert it. It is like, see, this is a card number 5. These are other cards. You have initially 5. You have placed it left. Then you are going with the 2. You are picking the card 2. What you will do with the card 2? You will compare it with 5. Right? If it is bigger than 5, so you will place it right of the 5. If it is smaller than 5, so what you will do? You will place it left of the 5. As we know that 2 is less than 5, so we'll shift 5 to right and insert 2 at its index, means that index is 0. So the new array would be like this. It would be 2 comma 5, and in this there would be 4, 6, 1 and 3. Now index changes to 4, right? What will happen? I have to insert what? I have to insert this 4 in this array. So I have to make a comparison. Make a comparison of 4 with 2. It is like you are picking now card with number 4. So what will you do? You will simply compare this 4 number card with the card 2 and 5. So you will simply do what? You will simply compare this 4 with 2 and 5 and place it accordingly. So after comparing, I will say that it is pass 2. Now I am doing this pass 2 when I am comparing this. Let me write over here. It is pass 2. So for pass 2, I am comparing 4 with 2 and 5 and placing it in proper position. So it would be 2 comma 4 comma 5. And the second part of the array would be 6 comma 1 comma 3. Right? Then it would be pass 3. And in pass 3, what I will do? I will simply write this was I is equal to 1, this was I is equal to 2, and now I is equal to 3. That would be 6. So I'll be comparing 6 with 2, 4, and 5. So what will happen? I will place this 6 at its appropriate position. So that would be like 2, 4, 5, and 6. Then the remaining array is 1 comma 3. Are you getting it or not? Now it would be another pass 4, right? So in pass 4, what I have to do? It is I is equal to 4, means the element is 1. Compare this element with all these 4 elements in the sorted array and place it, insert it in a proper place. So the proper place for it would be simply 1 comma 2 comma 4 comma 5 comma 6, and the last element is 3, that is the pass 4, and at that time when we write it would be 1 comma 2 comma 3 comma 4 comma 5 comma 6. So this is the final sorted array, and this is how insertion sort is actually working. Got it or not? I will discuss it later, Gen AI and other things. Let us concentrate on this class only right now. Okay, so it was 1, 2, 3, 4, 5, 6. If any questions till now, please ask. Yes. Have you got it or not? As we have to compute the complexity of it, time complexity in best, worst case, and average case. So you have to tell me what is the complexity in best case. And first tell me when is the best case for this array. When is the best case? Yeah. When is the best case for this array? when elements are sorted. See, it is simple. I am explaining it again. This was the list for me, right? And I have to sort this list, this array. The elements in this array I have to sort. And in insertion sort, I already told you it is like arranging your cards. For example, I am giving you these cards, and these are the numbers on these cards. How will you arrange those cards? It is simple. You will simply do what? What will you do? You will simply build the sorted list one element at a time. For example, if initially it is 5, then you will take the second card, compare it with 5. If it is greater than 5, you will place it after 5. If it is less than 5, you will place it at the first place. Means you will insert it at the first place, right? Now you have these two cards and the remaining card. Then you will take another card with number 4. Then you will compare this number 4 card with already sorted cards 2 and 5. You will check the place of those two cards and insert this 4 accordingly. So you will place this 4 number card between 2 and 5. So it becomes 2, 5, 2, 4, 5. Then again you will pick 6, compare it with the sorted list. Then you will pick 1 and finally 3. So we are doing it in passes. Like yesterday we did that, those two algorithms in passes. So here also, in the first pass, what we did? In pass, first we compare this 2 with 5 and place it over here. Then in the second pass, we compare 4. We took the element 4 and compare it with 2 and 5 and insert it in a proper place. Then in the third pass, we compare this one, no, 6. Then compare it with 2, 4 and 5 and place it in its place. Then we compare 1, then finally we compare 6. So this way we have sorted all the elements. Now it is time complex. See, now I told you when is the best case. The best case is when all the elements are sorted. Means we have a sorted list itself. If you have a sorted list, that is the best case, right? Now what is the complexity in that case when your list is sorted? Yes, what is the complexity in that case when your list is sorted? Can anyone? Log n. Why are you always saying log n? Log n is only then when the flow growth is logarithmic, means when the list is being divided at each step. Only then the complexity comes log n. Order of n, right? Order of n is the correct answer. But how it is order of n? Can anyone? How it is order of n? The list is sorted. So what are you doing? Yes. Can anyone tell me? Yeah, please be quick with your answers. Why is it order of n? Anyone? I'm waiting for your answers. When the list is sorted, already sorted, and you want to perform this insertion sort. Yes. Anyone? See, it is simple. You don't have to perform any kind of shifts. For example, if I have this array, let us take another array, already sorted array. Like suppose this array I have. 1, 2, 3, 4, 5, 6. This is the array. I want to perform insertion sort. What I will do? I will first select 2. compare it with 1. So I will get 1, 2. Right? Then I have 3. Compare it with 1, 2. So it is simply 3. Means I don't have to perform any kind of shift. Then I will take 4. So compare it with 1, 2, 3. So it will be simply 1, 2, 3, 4. No shifts. Similarly, 5, compare, no shift. Similarly, 6, no compare and no shifts. Means you don't have to perform any kind of shifts. So that is why the complexity is of the order of n. It means only one comparison is made in each pass, in each iteration. So no need to perform any kind of shift. That is why we are just saying the best case complexity of this insertion sort is of the order of n. And in worst case, what you have to do? You have to first check, compare, and then reshuffle the elements. So in that case, it is of the order of n, means in the first step. Simple. See, in the first step, what you will do? You will do one comparison. If it is reversed, like suppose here, in the first step, you will do one comparison. When you are in the second pass, you will do two comparisons. Similarly, in third pass, 3 and 4 and so on. So when you add all these, they turn out to be n into n plus 1 divided by 2, means of the order of n square. So that is why we are just saying the complexity in worst case is of the order of n square, because in each pass, in the first pass, we have only one comparison, means first element and the second element. In second pass, we have first two elements and the third element of the array, compare it. Then in the next pass, next element, all the elements in the sorted part, compare them. It's like cards in your hand. When you sorted 4 cards, you are taking this card. If they are like in a sorted manner, just place it next. No need to shuffle. But when this card you have to place in between, so you have to compare this card with each one and you have to perform the reshuffling. So that's why we are just saying after each step you have to perform these number of comparisons. So when we add all these comparisons, they turned out to be of the order of n square. So this way we are just saying the complexity of this insertion sort is of the order of n square in worst case and of the order of n in best case, because if the array is already sorted, you don't have to perform any kind of shuffling. In each pass, just compare and place the element. Hope it is clear. Yes. If any questions, please ask. Now we'll go to the programming part of it. It is clear or not? Yes or no? Just type in the chat box so that I will proceed further. Just your confirmation so that I can proceed further. Okay, great. Now let me share the screen for online compiler. Okay, I hope it is visible, online compiler. See, this is the algorithm for insertion sort. Same algorithm that for that we did this now. Example, if you check it. Again, we'll be explaining it. Those who have not clearly checked it, check it again. See here. We have an array, right? We are just first checking the array length. If it is less than this, first element means only one element in the list, that is already sorted. That's why we are performing this condition. Now we are just setting this ARR of I to key, means whatever the element you are checking, that we discussed in the previous example. For example, if you have like this 2, 3, 1, 5, 6, 4, if it is like so, so first element is this, we are leaving it as such, then we are taking this key, this we are comparing with this element, then we are comparing it. After comparing, we are placing it at a proper place. Then we are taking this. In the next pass, we are taking this element. Then in that pass, we are comparing this one with this list, with the already sorted part. Again, we will place it at the appropriate place. Then we will take another element in the next pass. Then compare that element with all the elements in the sorted list and place it appropriately. Similarly, we will take this next element 6, compare it with the sorted part and place it appropriately. Then we will take the last element, compare it and place it. So that is the simple insertion sort. Take it, compare it and insert it. So when we go to the algorithm, simple here also, we are comparing it, then we are decrementing the loop. Means we are taking the loop from here to here, j minus 1. For that, j greater or equal to and ARR of key is greater than equal to key. Simply then what we are doing? We are simply reshuffling the element. So this way, when we run it, it will return the sorted list. Okay, see this way. And I have explained it how it is actually working. And we have also explained the complexity of it. Okay, fine. So next sorting technique is, can anyone guess what could be the next sorting technique? Okay, now let us go with the merge sort. It is an important sorting technique. And I guess it is it is having somehow less complexity than other algorithms. Right now, what is merge sort? Yes. What is merge sort? Can anyone explain it? Yes. Okay, what are you answering? Combine is the sorting the elements till it becomes individual. Divide and conquer. Great, we are using it. Divide and conquer algorithm we are using for it. It is a popular sorting. That is a divide and it breaks array into house. Great. Okay. Thank you for answering the question. With this, I just find you that you are interactive in the session. That is the reason why I am asking these questions. And it has to be there in order to make the session as interactive, right? Good to see your answers. Thank you. Yeah, some people are also writing the complexity as well. Let us go to that part later. Okay. See, as you already answered this question, merge sort simply uses divide and conquer algorithm. So we will say merge sort is a divide and conquer algorithm. That divide is the array. Means right now, for example, we were just having the array like this. I guess this was the example 1, 2, 3, 4, 5. Let me write it like this in any order. So this was the array till now. Until now, we were not dividing this array. Isn't it? Simply we were using some technique, some sorting technique, either comparing first two, making a bubble, either selecting one, then comparing it with all others, either taking some index, taking another element, comparing this element with the already sorted array, then inserting it at a proper place. So that was the procedure till now. But what we are doing in this algorithm is actually we are dividing this array. See, here may be, because whenever I am saying dividing the array, maybe the complexity come in terms of logarithmic. Remember it. Till now, we didn't do anything related to dividing an array. So that's why till now, none sorting techniques till now logarithmic came. It was either n or n square. That's it. But whenever I am taking into consideration that we are dividing the array, so possibility is there that log n might come. Now, how will it come? Whether it will come n, log n, whatever, that will be seen in the later part of the problem. But possibility is there. Whenever I am just saying dividing the array, so it means it can be logarithmic process. It can be a logarithmic progress, right? So we are dividing the array into two halves, or I can say into halves recursively until each, see, whenever I am saying array, we are dividing this array into sub arrays until each sub array has one element. Means we are dividing, if we have got like suppose 10 elements in an array, right? We are dividing it into 2, 6, 5, like suppose. Then this 6, 3, 3, this 5, 3, 2, then this 3, 2, 1, again 2, 1, then 1, 1. Means we are taking it to the individual level, means individual element. Each sub array has got one element. Till then, we are dividing the sub arrays. After dividing, after reaching at the elementary part, means after reaching at the base level, root, this child level, where each sub part is having only one element, then we compare them and merge them again. That is it. So dividing until each sub array has only one element, then it merges the sub arrays in a sorted manner. Got it? Simple. Array, divide them till each subarray has one element. Once at the root, this child level, at the last level of the tree, if it has got only one element, then compare them and merge them. That is the technique that we follow in merge sort. That is why it is called as merge. Merge means after dividing, combine the solution. So, how many steps we have here? First one is divide it, second is sort it, third is merge it. This divide, sort, and merge. These are the three steps, major steps that merge sort is taking. First one is divide the array, or I can say split it into two halves. Then recursively sort each half, then merge the sorted halves. So these are the steps that we are following while performing this I can say merge sort. Let us take an example. See here, I have already used the list. Let me divide this list into two halves. Okay. So the two halves would be what? Let me take the first half as 5, 2, 4. And the second half as 6, 1, 3. So this is the, let me take it a bit here. Okay. Is it fine? So after that, what I will do? I will divide it further. Right? When I will divide it further, what will happen? So left part is 5, 2, 4. So I will divide it into, like suppose, let me take 5 and 2, 4, or 5, 2 and 2, 4. I will divide it into 5 and 2, 4. And also the second part as 6 and 1, 3. So this is the second division, right? After that, what I will do? I have to divide the further arrays which are containing more than one element. So here I will be dividing what? 2, then 4. 6 is there, then 1, 3. So at the final level, I have like this. It would be now 6, and here it would be 5. So this is the array that I have at the bottom. Now I have to compare all these elements, right? Because each array is now having only a single element, isn't it? So what I will do, I will this see divide I did, sort I didn't did till now. So first I will sort it. So for that, what I will do, I will sort this part individual array and this part. Later I will perform the merging. So here I will do like this. It is array 5. Then the after merging, this array will become like 2, 4. Similarly, this array is 6, and after sorting, it will become 1, 3 because they are already sorted. And in the next step, what I will do, I will sort these three 5, 2, 4. It will be 2, 4, 5, and the right subarray would be 1, is 1, 3, 6, right? And when I combine, when I merge the total array, so it would be what? It would be the final array. Means when I merge the both sides of this array, it would be 1, 2, 3, 4, 5, and 6. So this is how do we perform merge sort. Divide it, sort it, and merge it. So this way we are actually doing what? We are performing the merge sort. Hope it is clear. Yes or no? Yes. If you have any question, you can write. Yes. Answer. Okay, fine. 613 sort 2. Yes, great. So I hope you are now aware how this merge sort is actually working. Simply again I am repeating 3 techniques: divide, sort, and merge. And I have shown you with the help of this example. So there is no doubt, I think you can get after explaining this example. It is very simple and I have done it in an easy manner. How to do dividing and how to do sorting. Like this I have divided, then I have divided like this I have divided like this, then at the individual level, right? Like then I have merged them like this, these two, then I have merged them here, again I merged these, and finally I got the sorted list with the help of merge sort. Okay, now what about complexity? What about complexity of merge sort? Yes. If you remember, we have also written the recurrence for merge sort previously. Order of n. No, it is not order of n. Can anyone guess it? No guesses. You have to now think about it. The very basic step is divide, isn't it? For divide, the complexity is what? What is the complexity for this division part? Simply, it is log n. So for this first part, it is log n, isn't it? For this part, I will say it is log n. Because there are total number of n levels for which I am dividing it. Like in the binary search, or I can say like in any kind of a tree where you have got n levels. So here I am dividing it, so the complexity is log n. Now we have the merge phase, right? And at each level, we are actually doing what? We are actually merging these. And when we merge these two sorted arrays, it takes the time of n, or I can say order of n, right? So merging two sorted arrays takes order of n time in total, means in total across all sub arrays. So that time is order of n. Right? So if you remember that this na recurrence relation, can anyone write a recurrence relation? If you remember, it is T of n. See, actually I am here, you will get clear what are the different variable in this. A T n by b plus f of n. Now what is this a? Yes, what is this a? Can anyone? What is this a? See, I am correlating the things, and with this, so many concepts are becoming clear. What is this a? Am I audible or not? Yeah, am I audible? You are not responding. I have written a recurrence relation. I am just asking what is this a in this recurrence relation? A is the number of subproblems. What is n by b? N by b is the size of each subproblem. And what is this f of n? If you have heard, if you have attended that class, it is simply the work done in doing other things apart from this division. Because this is recurrence for divide and conquer. So this f of n is actually the work done. When we solved the recurrence, at that time we discussed it. This f of n is the work done. So when we take the case of this merge sort, for division we have log n because it is 2t n by 2, I guess. Right? Then the remaining work is n, means by the work done in merging all these sorted arrays. So for that it is n, and for this it is log n. So when we compute the total complexity of this merge sort, it turns out to be of the order of n log n, and there is no need to cramp this result. Simply you have to what? You have to now analyze it, and I hope it is clear. If you have any doubts, please ask. Yes, is it fine, clear or not? Yes or no? See, it is simple. Merge sort is simple, and you know why it is complexity is of the order of n log n. No, complexity for binary search is only log n. You don't have to merge the result in binary search. But here what we are doing? First we are dividing the list here. Till now it is log n. But at the same time we have to merge the result. That is why the name merge sort is there. So for this part it is log n, and for merging part, the work done f of n, it is of the order of n. So it is n log n. Yeah, for merging n comes, because actually it is the work done that we did in recurrence relation. So totally it becomes n log n. Otherwise, for the divide part, it is only log, because again I am repeating, whenever we are dividing, it is logarithmic, growth is logarithmic. But apart from dividing, there is one more part of the merge sort, that is merging it. So dividing plus merging, or dividing and merging in total is n log n. And at the same time, if you remember this recurrence, it is 2t n by 2 plus n. So that's why it was becoming n log n. Okay, any questions? Any questions? You want to ask something? If it is clear, just write your message. If it is clear, type yes or no. Yes or no. Second part means merging part. Okay, this was the array, right? I'm repeating it from the start. See, this was the array. The first part is simply divided. I divided into these two sub-arrays. Further, I divided these into these two sub-arrays, right? It is simple. Then I divided this into 2 and 4 and this array into 3 and 1. Now we have got individual elements. These. Each sub-array is containing only one element right now. So till now the complexity is log n, because we have divided the array, and for any division, whenever you are performing a division of the array, the complexity turns out to be log n. Now I have the second part. Second part is merging. See here, I have to merge these. Once they are sorted 1, 3, merge them. So they will merge out to be 1 and 3. Similarly, these two, merge them, these arrays. They'll turn out to be 2, 4. Now merge these three. Sort and merge, right? They turn out to be like this. These turn out to be like this. And finally, when we merge them, it turns out to be this sorted array. And for this merging part, the work done is, it is n. So in total, the complexity becomes n log n. So this is the total complexity of merge sort. See here, I am dividing, if left is right, right is right. So these things we did. I hope it is clear now. Yes or no? Okay, so let us go to the, let us proceed. Let me, I hope you are like, now it is clear to you, then I will clear my screen. This na drawings that I have drawn, example. Okay, fine. And in best case it is n log n. In average case it is n log n. And it is worst case. Can anyone tell me the complexity of merge sort in all the cases? Yes. Complexity of merge sort in all the cases. Yes, it is in all cases it is n log n. Because it hardly matters on the order. If the array is in sorted list, still it has to perform the division. After dividing, still it has to merge it. So it hardly matters. So that's why we are just saying in all the cases the complexity is n means for work done and log n means for dividing. That's why we are just saying the complexity for merge sort is n log n in all the three cases. Right? So it is only the merge sort. Remember it. That does not degrade to n square complexity. Because every sorting technique, कोई भी sorting technique आप देख लो, worst case में they are degrading to the complexity of n square. But it is the merge sort only that is not degrading to n square complexity. So it remains n log n. If you talk about this quicksort has got also this n log n, but sometimes that degrades to n square. But it is the rarest algorithm among all sorting algorithms that does not degrade to n square complexity. Remember it always. It is always predictable. And what would be the space complexity? Can anyone? What can be the space complexity? Remember it is n. And can anyone guess why it is n? Because merge sort requires extra, I can say, space to store these temporary arrays which it is creating during merging. While merging the arrays, it requires extra amount of space. So each array is copied either into left or into right. Although the depth is only log n, you know it. But the temporary arrays require order of n memory. Remember it. Keep it in mind. Although the depth is log n only, but these temporary arrays require n memory in total, order of n memory in total. Right? So remember, n log n is the complexity and order of n is the space complexity. Fine? Any questions? Any questions? If any questions, you can ask. Regarding time complexity, can you write the recurrence relation of merge sort in chat box? I just want to check whether you know it or not, or you have forgotten the recurrence relation of merge sort. Right? Type the recurrence relation of merge sort in chat box. Good. See, again, you don't have to remember it now. As per the problem, if you know now merge sort, right, and you also know the recurrence relation general format. See, technically I am speaking, logically, because during the start, during each session, I'm always telling you that don't cram the things. Just have a concept, think logically, and things will be done. Otherwise, I don't know what things you want, you have to remember. Think logically, simple. The general form of recurrence relation is ATN by B plus F of M. Simple. That's it. That you have to remember. Only thing. Now merge sort is there. Simple. Merge sort is simply we are dividing the array, then merging it. Now, as we know in recurrence relation, A is the number of subproblems. Is the number of this ATN by B. Number of subproblems n by b is the size of each subproblem. Now, what is the number of subproblems in the merge sort? It is 2. Always we are dividing the array into 2. So it is 2, 2t. What is n by b? B is number of size of each subproblem. It is n by 2. Means whatever is the list, uska half. So it is 2t n by b plus n. What is the work done in merging the list? It is simply n. So it is 2t n by 2 plus n. Right? And you can solve it using master method, or you can simply check the complexity of merge sort. Either writing down that we require logarithmic steps to divide, then we require n to merge the list. Means work done is n, number of steps to divide the list, it is log n. So that is simple. Everything becomes clear about merge sort. Nothing to remember, nothing to cramp. Simply concept and that's it. And in all the cases, you require n log n because it hardly matters whether the list is sorted or not, because you have to divide and you have to merge. And space complexity is order of n because we have to keep the intermediate results while merging in the memory, in the story. So that's why it is of the order of n. Hope it is clear. Any questions you can ask, then we will go for a break. After that, we can have quick sort and we will see recursion. Any questions? I will give you 1 minute if you have got any questions. Okay, everything clear? Type yes or no if everything is clear. Great. And I hope you are getting the things only then you are, I guess, only then you are typing the messages if you are having the concepts. Great. Okay, fine. Let us go for a break for 10 minutes, then we'll be back. What is the time? It is 22. So 2010 we will be back. Is it fine? 10-minute break. Not 10, it is only 8 minutes. Let it be. So till then, refresh yourself, get your concepts revised in the mind itself. Then we'll start again. Okay, hope you are back. Yes. Are you there? Yeah, let us continue. Are you there? Okay, this is the algorithm for merge sort that we discussed, and this is the program for merge sort. Let's explain this program as well. It's not that difficult because we already did it. Here again, we are creating a class of merge sort. Then we are just passing array left and right. Then we are just checking if left is less than right. Then we are just finding the mid, left plus right divided by 2. Fine. Then again we are going for this method merge sort. And if it is like left is less than right, yes, we are doing base step, and accordingly we are just changing the mid value, mid plus 1 and right. Similarly here. So this way we are actually doing what? We are using the merge function. Here we are actually dividing it, and here we are merging and then making the comparison. So here it is log n, here it is n. So this way we are doing the merge. If we run this program, let me check it. So it will simply sort. Okay, I hope this is visible. See here, I have run this program, merge sort, and this is the sorted array. Okay, so I hope it is clear. We have discussed it logically how it is actually working. So this is the program for it. Let us go back to this presentation screen and we will explain now quick sort. Yes, what is quick sort and how it is working? Yes. Yeah, I'm waiting for your answer. What is quick sort? I'm waiting for your answers. Am I audible to you or not? Okay, sorry, actually I forgot to put on my headphone. Sorry. Okay, I guess now I am very clearly audible to you. Sorry, actually I forgot to put on my headphones. Thank you for reminding me. Okay, so what is quick sort? How it is sorting the elements? Give your definitions, what you know, and make sure you will not see. Don't try to copy the things from here and there in this platform, because I will tell you one thing. See, remember it as well. Here there is no exam, right? And whatever you type, type it from your mind. And when you type it from your mind, if it is right, it will be like make a blueprint on your mind. If it is wrong, or if it is like somehow right, wrong, or in between, it will be overwritten with a correct definition. Either I can provide, either someone in the chat box can provide. But the thing is, don't copy things while answering the questions over here, because you will answer. There is nothing worry about that. If you will answer incorrectly, and I want your incorrect answer so that we can rectify those answers. So better is to speak up your mind, whatever the definition, whatever the concept you have in your minds, try to give that answer only. Don't copy things and that then paste in the chat box. That is not the good thing. Right here, it is not an exam. You won't be graded on your answers. Right? So better is to whatever is present in your mind, whatever concept definition you have got in your mind. So better is to speak that. And if that is correct, that would be like printed. If that is incorrect, that has got some that wants some correction, we are here to correct that, and that will get rectified, right? So keep that thing in mind. So what we are discussing about quick sort, right? So again, quick sort is what? Divide and conquer technique, right? It is making use of divide and conquer again. So here also, what we are doing, selecting the pivot, right? We are selecting the pivot element, then comparing with the rest of element is good. We can select one element at pivot, right? Good. See, also here, the definition which you are giving, it is absolutely fine. So it is actually a divide and conquer algorithm. And in this algorithm, what we are doing, we are here selecting a pivot element, right? Here in algorithm, set pivot, etc. So what I will tell you, simply we are here selecting a pivot element, right? And then we partition the array. After selecting the pivot, we partition the array. And we are doing partition in such a way that, see, after selecting pivot, we partition. And we partition the array on the basis of this pivot element, right? And if the elements, I can say like suppose elements are less than pivot, what we'll do? They will go to left. If the elements are greater than this pivot, then they will go to right. So this is simply the algorithm. Whole thing revolves now around this. Select a pivot, perform the partitioning on this pivot. Elements less than pivot, they will go to left. Elements greater than pivot, they will go to right. So this is the quick sort. And now we will explain it. It is like now, it is right now, it is only a theoretical concept, but how it is working. Now let us take the example. I will again take the same example, those elements which I was taking. Let me choose a different color now. So we have got elements like, suppose, let me write here. I hope it is visible whatever I am writing. So let me choose this array again. 5, it was like 2, 4, 6, 1, 3. So this is the array. Five, 2, 4, 6, 1, 3. This is the array, right? 5, 2, 6, 1, 3. Okay. Now first what I will do, I will choose a pivot. See, you can choose pivot either a first element or a last element. So here let me choose the last element in the next example. I can take another example where I will choose the first element. So for the time being, I am choosing this as pivot. Which one? I am choosing this 3 as pivot. Let me choose a different color again. So this 3, I just want to make it as pivot. So pivot is equal, like suppose I will write P is equal to 3. And pivot means pivot is equal to 3. Now, go here. Perform the partition based on what? Based on this pivot. So compare the elements. Let me connect the charger first. Now compare the elements. Elements less than 3. What are the elements in this list that are less than 3? It is 1 and 2. Right? So it would be 2, 1 and elements greater than 3. They are what? 5, 4, 6. So these are the two lists. Right? And the final list is what? It is 2, 1, 3, 5, 4, 6. So this is the list now. Because based on this pivot 3, I have partitioned it. And based on this, the 3 is at the correct place. Right? So now the 3 has got its correct place. And on this 3, I will be dividing the list recursively. Right? If you got this step, now you can do any number of steps and you can do any number of partitioning. It is simple. I hope it is clear. If you want me to repeat it, I will repeat it. See, only this thing, only this step, this is important and this is like, where most of the students, they fail to understand why it is like this. If you got it correctly, if you got it conceptually, then it is fine. If not, I just want it. If you want me to repeat, I will repeat. But this step is important. Yeah. Okay. Let me repeat it again. Let me undo the steps. Okay. So this is the list. Right? And the very basic step, see, I have to choose the pivot element. I am choosing the pivot element, and it is up to you how do you choose the pivot element. There is no hard and fast rule for choosing a pivot element. In this example, I am choosing 3, the last element. In the next example, I will choose another element or maybe the first element. So this is the pivot I am choosing. After choosing the pivot, right, partition the array. And how do we partition? Means how do we divide the array? Based on this. All the elements that are less than these 3, they will go to left subarray. And all the elements that are greater than these 3, they will go to right subarray. Means based on that, the elements would be the elements that are less than 3. I can say right like this. Less than 3 elements would be what? 2, 1. Right? And greater than 3 elements would be 5, 4, 6. That it be now bracket this. So this is till now elements left less than pivot and elements greater than pivot. Now I will combine it again. The total final array would be like this. 2, 1, pivot 3 appropriate position, 5, 4, 6. So this is the array now. And after this step, one thing is clear, this pivot got its exact position. This 3. This got its exact position. And based on this pivot position, now I will divide the array. And I hope it is clear. Right? So this becomes my left subarray and this becomes my right subarray based on this pivot position. And after this partitioning, one element is placed correctly. That is this pivot. So pivot has got its position in the sorted array. Hope it is clear. Right? You want me, if any doubts, please ask. Is it clear now? Any doubts till now? See, after that it is simple. We will recursively repeat these steps. Is it clear? Okay, fine. See, now I have got two arrays, sub arrays. One array is containing this 2, 1, and another one is containing what? This 5, 4, 6. Right? This is the pivot. Okay. Now I will take the first sub array. This one. 2, 1. Right? And here I will do the same that I did with the original array. I will choose a pivot. Which pivot I will choose? I will choose a pivot 1. Right? Then I will compare this one with all the elements. And I will place the elements that are less than 1 to the left and elements that are greater than 1 to the right. So the elements that are less than 1 in the list, there is nothing. So I will write 1 itself. And elements that are greater than 1, there is only one element, that is 2. So this 1, 2 is the left subarray and it gets sorted. Right? So it has been placed correctly. There are only 2 elements in this subarray. Now I have the right subarray. Which subarray? Right. The elements are, what are the elements in that subarray? They are 5, 4, 6. Now I will choose pivot again. Which element to choose as pivot? Yes. See, it is simple. It is already sorted. Let me choose array like this. Let us suppose the elements were like 6, 5, 4. It is already sorted, so it won't be explained clearly. So this is the sorted, this is the array. And I have to sort it. And what I will choose? I will choose a new pivot. What I will choose as pivot? I will choose pivot 4. Then I will compare these elements with 4. The elements that are less than 4 will be placed in the left subarray and the elements that are greater than 4 will be placed in the right subarray. So the elements less than 4, what are those? Nothing. It is empty array, like suppose. And the elements greater than 4, it is 6, 5. Right? Now the final array would be, it would be 4, 5, 6. And which element is here correctly placed? It is pivot, that is 4. Now I will divide the array based on this pivot. So what would be the new division? Yes, based on 4. So it would be an empty array here, right? Because there is nothing in the left part of this, and the array with the elements 5, 6. Right? So what will I do? I will choose a new pivot in this array. The pivot is actually 6, 5. The new pivot is 6. I will choose 6 as pivot. Then I will check all the elements that are less than 6, put them left, and all the elements that are greater than 6, put them right. So it would be 5, then 6. And this is the sorted array now. 1, 2, 3, because it was chosen as pivot, 4, 5, and 6. So the final sorted array would be 1, 2, 3, 4, 5, and 6. This is how do we sort in quick sort. Hope you have got it. Yes or no? Just a quick thumbs up. If you got it, just a quick thumbs up. We'll take another example where I will change my pivot. I will change the pivot to first element and we will see more number of elements. Not these only 5, 6 elements, we will go to like 9, 10 elements. Yes, we'll take one more example and I will choose a different pivot right now. Okay, let me clear my drawings and let us take another example. I will take 9 elements, because if I will take more than 9, they will not also, they will take the screen more. Let me take the array 9, 4, 7, 1, 6, 3, 8, 2, 1, 2, 3, 4, 5. Yes. So this is the array. I want to sort this array, and the method would be what? Which method I will use? I will use quick sort. So here, the very first step is, if you remember the steps, what are the steps that we are taking? First, we are selecting the, here I will be writing. See, remember these steps. Select the pivot, partition the array based on pivot. Means while partitioning, you will do the elements that are less than pivot, put them left in the left side, and the elements means less than pivot, put them in the left side, greater than pivot, put them on the right side. So these are the steps. Now in the previous example, I choose the pivot as the last element, but let me choose pivot as the first element, and it is a good example. That's why I put 9th very at the very first place. So first element is pivot. Now after that, what I am doing, I have to partition this array based on this pivot. So for that, what I will do, I will compare all these elements with 9. The elements that are less than 9 will be placed in the left, and all the elements that are greater than 9 will be placed in the right. So pivot I have chosen as 9. So what will happen? All the elements that are less than 9, they will go to left. Means what are the elements that will go to left? All the elements. It would be 4, 7, 1, 6, 3, 8, 2, 5, right? And the last element, that is on the base of which I have partitioned the array, it is 9. That is the pivot. So this is now all the elements that are left than this pivot, they are left, and all the elements that are greater than this 9, they are on the right. So after partitioning, pivot ends up at the last index because it was the greatest element among the array elements. Right? So here now the pivot index moves to 8 because 9 elements are there. So the index goes to 8. And what is the right part of this array? Left part is this that we checked, isn't it? So this is the left part, whole array. This is the pivot. And what is right part? Right part is simply an empty array, nothing, because there is no element in the array that is greater than 9. So this is step 1 till now. And till now, which element is at the correct position? Can anyone tell me? Which element is at the correct position? Because after partitioning, one element occupies its final place. Which is that element? Yes, that is 9, because 9 has occupied its place. Again, now let us do the step 2. And step 2, what is the pivot that I will choose? Because I am choosing the first element as pivot. So the next element to be chosen as pivot is 4. Okay. So what will happen? Elements less than pivot, they move to left. Elements greater than pivot, they move to right. And what are the elements that are left less than 4? Simple. It is 1, 3, and 2. Right? And what are the elements that are greater than 4? They are, yes, 7, 6, 8, yes, and 5. 9 is already sorted. So these are the elements. Fine. Okay, when I combine this, What happened to it? Okay, actually, the elements greater than 5 are, they were like, yes, 7, 6, 8, and 5, right? So if I combine these, the new array becomes, what is the new array? It would be 1, 3, 2, 4 is already sorted, 7, 6, 8, 5. So this is the new array. And 9 is already there, that is also sorted. So in this array, 2 elements are already sorted. Which one? 4 and index 3 and index 8. So these are the two indices that are at their correct places. Okay, now we will be sorting what? I will be sorting the left part of the subarray, means this part. This part I will be sorting. See, this is the new pivot. Based on that, I divided the array, this part and this part. So the my new array would be which one? It would be 1, 3, 2. Isn't it? So the new array would be 1, 3, and 2, right? And right subarray would be, what is the right subarray? It would be 7, 6, 8, 5. Now let us first sort this left subarray. Choose the pivot. What is the pivot that I have to choose? I will choose 1 as pivot because I am choosing the pivot as first element. So based on that, I will partition the array. Right? While partitioning, what will happen? Element is less than 1, they will be moved to left, and element is greater than 1, they will be moved to right. So here it is, it would be 1, and less than elements less than 1, it is a null array. Right? Then it would be 1, and elements greater than 1, they would be in the right part of right subarray, that is 3, 2. Right? Similarly here, choose 7 as pivot. So when I choose 7 as pivot, elements less than 7 will be placed in the left subarray. Like suppose it would be 6, 5, and 7 is at the correct place, and the elements greater than 7, that is simply 8, and it is at this place. Then further, see, 1 is at its correct place. Now the subarray is 3, 2. Choose pivot as 3. I will go to this part of the array. If I choose 3 as pivot, so elements less than 3 would be at the left, and elements greater than 3 would be at the right. So what are the elements that are less than 3? So they are simply what? That is only 2, and 3 is at its correct place because it is pivot. Similarly here in this 6 and 5, I'll choose 6 as pivot. Elements less than 6 are to the left, and elements greater than 6 are to the right. So there are only 2 elements, means 5 would be to the left, 6 is the pivot. Similarly 7 is already chosen as pivot, and 8 is already there, and the element that was initially chosen as pivot was 9. So I guess all the elements are at their respective places. So this is the sorted final array. This way we are performing what? We are performing the quick sort. Hope it is clear. If you have any questions, please ask. And we are recursively doing this. If you have any questions, you can ask. If it is clear, then you can write your message. You can write a thumbs up if the things are clear. So this way we are doing the quick sort. I hope it is clear. Then I will erase the example. Then we'll go to the complexity part. Okay, only few people are writing. It means only these people are listening to the session, or only these people are understanding. What about others? See, when you write the message, it means that you are listening. When you will not write, it means that the people are not listening, or they are not understanding. Only two things are there. See, it is your choice. you can choose the pivot either as the last or as the first. That we have shown with those examples. That's why I choose two examples of pivot. Choose it as first or as last. And I have done it both ways. Yes, anything else? You must ask the questions. Okay, let me clear these drawings then. We'll go to the what I can say, the complexity part. Okay, and this is the program. If we run it, it is simple. I can run the quick sort algorithm. Okay, let me run this. First, I have to share your that screen. Java program, not this one. I have to go here. Actually, I have created these programs as per our examples that we are taking, right? So I'm just copying from there itself. Something wrong happens. If we check this program, see here, I guess we discussed it in with the help of example itself. Pi is equal to partition, then quick sort, array low, pi minus 1. So we did it, partitioning, how do we perform it, how to choose a pivot, how to compare pivot with all your elements. So all these things we did. Actually, we are comparing the elements with the pivot, and based on that, we are putting the elements that are less than the pivot to left and greater than elements to the right. Okay, now what is the complexity of it? Yes, what is the complexity of quick sort? Write down in the chat box. Yes, complexity, I guess. And log n, good. Okay, and log n, fine. So let us explain its complexity, right? I can say the complexity of quick sort is n log n. It is the best, right? The best case complexity of quick sort is n log n. Then we will do the comparisons, right? So it is best case complexity is n log n. Right, because we are choosing the pivot partition, then list elements less than pivot, greater than pivot, then recursively we are solving the both sub arrays. So in best case, it is what? it is simply n log n in best case, means it is of the order of n log n in best case, right? Because we are choosing this na balanced partition, means good pivots, and it is average is also of the order of n log n, right? So it means this, whenever we are just like doing the best case, we are actually dividing the arrays, I can say, into two halves, and those halves are I can say nearly equal each time, every time. Like suppose 10 elements, 5 5, every time 2 equal halves, and so on. So at that time, the recursion, whenever we are making this recursion, the depth of this recursion becomes log n, and work done means partitioning, comparing. Whenever we are partitioning, means then we are comparing the element with the help of this pivot, or the partitioning element. We also call that as pivot, means partitioning element, on the basis of which we are actually dividing the array. So we are actually performing the comparison based on that. For that, the work done is n. So it is n log n. Total work done is n log n. Are you getting it? So you will always remember, like when we say good pivot. Good pivot is simply when you are partitioning the array into two equal halves each time. Whenever your pivot is dividing the array into equal halves every time. So we call that as a good pivot. And at that time, the complexity turns out to be n log n, because for the recursion tree, for the depth of this recursion, the steps is log n, and for the remaining part, means work done per level, it would be n. Means partitioning and comparing each element. For that, it is n. So the total turns out to be n log n. And in average case also, it turns out to be n log n, right? And in worst case, what happens? In worst case, what is the complexity? Can anyone tell me? Yes, someone has already written it. It is order of n square. Good. So it is order of n square. Because see, when is the worst case? Whenever the pivot is always smallest or largest element. Like you see in the previous case, whenever we were taking the example of n. So it was the largest. So what I have to do? I have to put it to the left, then put it to the right, then left subarray remains empty. And the other subarray remains what? It remains n minus 1. Isn't it? So for that purpose, we are just saying it is not good depth. It is not good pivoting. So at that time, the tree that we are making, the partitioning that is happening, that is not balanced. Because in the left subtree, you have empty list, and in the right subtree, you have all the n minus 1 elements. Again, in the right subtree, if again happens, means if the pivot is either smallest or largest, so what happens? Again, either of the tree would be empty and other tree would be containing n minus 2 elements. And again, it will be unbalanced kind of a thing. So the recursion tree would not be a balanced tree. It would be a kind of, I can say, linked list. So there are all elements in that this subarray, and the remaining subarray is empty. In the next level also, one subarray is empty, another subarray is containing all the remaining n minus 1 elements, and so on. So this way, we are actually not forming a balanced tree. We are actually forming what? Kind of a linked list. So for that purpose, the depth is not now n this log n, it becomes n. Fine. So and work done is also n. So it turns out to be n square. So that's why we are just saying that in worst case, the complexity of this quick sort is n square. Because, and whenever quick sort is happening, when we are not, when pivot is not good, we will say that bad pivot, right? So bad pivot is give unbalanced splitting, unbalanced partitioning, and unbalanced partitioning means your one of the subtrees empty and other subtrees containing n minus 1 elements, because the pivot is either the largest or the smallest among all the elements in the array. So in that way, the array does not have the depth of log n. It turns out to be that the depth of the array is n, and the work done is also n, so the final complexity turns out to be n square. And I hope it is clear. If you have any questions, you can ask. And what is the space complexity? It is also, in best case, it is log n, and in worst case, it is n. For that previous example, for that previous sorting technique, means merge sort, there also it turns out to be n. And here also in the worst case, it is n because bad pivot. Any questions? Any questions? Okay, I hope it is clear. Just a thumbs up if it is clear. Yes or no. When the things are clear, just type your message. Because with that, I just came to know what actually is happening in the class. Okay, clear. Great. So I hope all the sorting techniques that we discussed, you have a good understanding of the sorting techniques now. And I guess we are clearing everything in the sorting techniques, complexity along with the logic. Okay, now let us do a comparison of all the sorting techniques. See, this is bubble sort. What is the complexity? And don't try to cram the things. Again, I am repeating. Just have the concept. Try to find out. Try to figure out the complexity. See, bubble sort. We are actually sorting using what? Using the comparison. Means first comparison, then second, then third, and so on. So we are getting the last element to the last. Then second pass, then third pass. In each pass, we are performing some number of comparisons. So when we add all the comparisons, they turn out to be n into n plus 1 divided by 2. So that is why the complexity is n square. Simple. No need to cramp, no need to remember it. And it has adjacent swaps that we discussed. So it is space complexity and it is a stable algorithm. Now the question is, what is a stable algorithm? Can anyone tell me? What is a stable sorting technique or stable this na? Yes. Can anyone tell me what is this stable? Stable sorting. See, it is simple. Stable means whenever the order is preserved in the sorting. For example, if you have got an array and the elements are like 3, 5, 7, 3, 3, 2, 1, 6. So there are two elements that are equal. If their order is preserved, for example, 3 is at this place and this 3. Whenever I am sorting it, it would be 1, 2, 3, then one more 3, then 5, 6, and 7. And if the order of these 3s is preserved, means first it would be this 3. Then after that it would be this 3. Then we will say the sorting is stable. Means it is actually preserving the order of the numbers. So that's why we are saying the sorting is stable. So for equal values, if you preserve the order, we will say the algorithm is stable. right? So this bubble sort is a stable sorting algorithm. Right, means here the order of these elements, equal elements or the same element, that is preserved. So why? That is why we are just saying this is a stable algorithm. And for selection sort also we did it. For this also we have a complexity of n square and it is not a stable algorithm. See, if you remember selection sort, what are we doing? We are actually selecting some element, then comparing it with all other elements. So in between the elements that are similar, that are equal, they may get swaps. Select a min plus swap. They may get swaps. That is why we are saying it is not stable. Similarly, for insertion sort, in insertion sort, the order is preserved for same number of elements, because whenever you have a card, if other card comes of this same number, for example, you have a card of 4 and another card in the unsorted list comes with the number of 4, you will place that 4 after the first 4. So order is preserved. And in merge sort also, here order is preserved, because what are you doing? You are first dividing the element. If you remember the example, then further dividing. If two elements are same, when you merge the elements, they will remain in the same order. It is not like you will change the order. So for that also it is stable. And for insertion sort also it is order of n square. For merge sort it is n log. Can anyone tell me what is the best case complexity of these algorithms that is different than n square among these three? I guess we discussed it. Among these three, the complexity is not n square in best case when the list is sorted. For what case the complexity was n? Yes. Am I getting the answer or not? No, not quick sort. I'm talking about bubble sort, bubble sort, insertion sort, and selection sort. Among these sorts, all three have worst case complexity of n square. For which case, for which sorting technique, the complexity is of the order of n in best case? Yes. Yes. Am I getting the answers? No. Yeah, for best case, in case of bubble sort and insertion sort, it is order of n. Because whenever you have the sorted list, in bubble sort also you have only perform the comparison. So whenever you go further, you don't have to do all the passes, or in each pass you have only one comparison. So that's why in best case the complexity is order of n, and in insertion sort also the complexity is order of n, that we discussed. But in case of selection sort, the complexity is n square, because every time you are selecting an element, then comparing it, whether the list is sorted or unsorted, at that time you have to do what? You have to compare with all the elements. So that is why for selection sort, the complexity is of the order of n. Good. Okay. Similarly, for this quick sort, this is the complexity, and for heap sort, this is the complexity. Okay. See here. Again, I have written it in all the three cases that I checked. See, in best case, this is it, this is it. But for selection sort, it is worst, it is order of n square in both cases. In all the three cases rather. But for these two, it turns out to be order of n only in the best case for bubble sort and select sort. And try to logically think about it, not like kind of cramping. For merge sort, it is n log n in both cases, or I can say rather all the three cases. For quick sort, it is n log n, and in worst case, it is n square. That we discuss why it is like so. For heap sort, we didn't discuss it. It is n log n, n log n, and n log n. Remember it also. For counting sort, we also didn't did it. Counting sort is not that important. Radix sort is also not that important. And all these three we didn't. We actually did these sorting techniques. So for this, we have done the complexities and all other things, right? And I hope you have got the concept. If you have any questions, you can ask me in the chat box. Then we will wind up the session. Okay, any questions? The window is open for you for the questions. You must ask the questions. I'm not getting that questions from your side. I don't know why is it so. Either you are not understanding or you are not listening. Only two cases are there. Yes, any questions? Okay, fine. So is it clear all the sorting techniques? And I hope you are making a real comparison among all the sorting techniques. Which sorting technique is working which way, what is the complexity, and how the complexity is like log n log n square. How is selection sort? You please check it again. It cannot be of the order of log n selection sort. You please check it again and come up with a solution. If that is the case, please share it with me. I will check it again. But I guess for selection sort, it cannot be like this. You come up with the solution, how it is log n of the order of log n. Then we'll work out on that. Okay, someone is saying that selection sort. Okay, let me. Selection sort is working, but means we are selecting the smallest element from the unsorted part and swap it with the first sorted element. I guess my screen is visible. Let me explain it with an example again. Let me take a list of these elements. Like suppose any 29, 10, 14, 37, 13, and so on. See here, what I will do. I will find the minimum element among all these. Right? I will select it. That is 10. I am finding. Okay. This is the unsorted array. And I will find the minimum at index. Like suppose 1, 0 and 1. Right? Yes. Then what I will do? I will swap this index with index 0. This is the pass one. Find the minimum. Swap it with the first element. So when I swap it with the first element, the new array becomes 10, 29, 14, 37, and 13. Right? This is pass one. And in pass second, what I will do? I will sort this part because till now one element is at the right place. That is 10. Now I will sort this part of the array in the second pass. Right? From index 1, this index. Now I will find the smallest element in this part. What is that smallest element? So obviously it is 13. So I will pick this 13. That is at index 4 and I will swap it with index 1. Select this and shift and swap. So the new array would be now what? It would be 10. Now I am swapping 13, then 14, 37, and with this 13 I swapped 29. So this is now the array after pass 2. Now in pass 3, what I will do? I have this unsorted array now, isn't it? The remaining part. This is now unsorted array. What I will do? I will check this 14. I will select the minimum among these. So the minimum is what? Minimum is 14. So it is at the right place. So there is no need to swapping. Now at this point of time, the array is simply 10, 13, and 14, right? Then the remaining part is 37 and 29. So what I will do? I have now this part of the array. Find the minimum in this part of the array. And if it is like not in a correct place, swap that. So it is at the final place and it is like this. Then the final array would be 29. It is the remaining element. So with this way, I have sorted the array using selection sort. So it means at every step, I am picking the element, means selecting the element, then swapping. Again, I am selecting, then swapping. Again, I am selecting, then. See here, if you check this part of the array, from this point, the elements were sorted, isn't it? But still, I have to compare. I have to make the comparison. That is why in selection sort, the best case complexity is also n square. Although the elements are already sorted, still I have to look for the minimum. I have to compare the elements among each other. So that is why it is complexity turns out to be order of n square. Hope it is now clear. Yeah, just confirm me. Is it fine now? There are so many sorting techniques. See, if we discuss about shell sort, heap sort, other sort, then it will take 3-4 lectures more. So you just try those sorting techniques by your own. These are the main sorting techniques that I have discussed in last 2 sessions, today and yesterday. Okay, so I hope it is clear. If it is clear, just give a thumbs up or just type your message. Okay, then let us wind up the session over here. If you have any queries, come up with your queries, questions. We'll try to answer in the next session. Till then, take care. Bye-bye. Good night.
Yeah, thank you, sir. Thank you, students. We'll meet again by tomorrow at 7.
Thank you so much.